Good afternoon and welcome to everyone. This event is organized by the Consulate General of Italy in Houston. I am the scientific attaché. And first of all, I would like to thank the Consulate Generale and my colleagues for their support.
This afternoon, it is a pleasure to have as guest speaker Professor Stefano Leonardi of the Department of Mechanical Engineering, University of Texas at Dallas. His research interests are in turbulent flows over rough walls, heat transfer, turbomachinery, superhydrophobic surfaces, wind turbines, cardiovascular flow, wildfire propagation, and oceanography. His presentation will be on a very interesting topic: analysis and optimization of wind farm performances. The theme of energy is a key and strategic point of our times.
So it is a pleasure to give the floor to Professor Leonardi, and at the end we will have a question and answer section, so you will be free to ask questions and comments.
I'm Stefano Leonardi, and I'm at UT Dallas since 2013. I'm the educational director of UTD Wind, which is a center in wind energy. And most of the research I'm going to present today is done by my graduate students. Some of them are Italians from Politecnico di Bari, Università di Pisa, and Università di Vienna. And we are funded by National Science Foundation. And this WinStar is a university, industry university cooperative research center that is also funded by National Science Foundations, and we have companies that are members of the center. They pay a membership fee. Some of them are in Houston, and they decide which research we should do. So, in a way, to do more applied research, not just as a kind of a mission, but really something practical that is of interest to these companies. Please feel free to stop me at any time. Let's have an informal and dynamic environment. We also need to acknowledge, I do mostly numerical simulations, so we have a very efficient supercomputer center in Texas. Is the Texas Advanced Computational Center in Austin, as part of UT Austin, and they provide us computational time to do all this research. So today I'm going to talk about the outlook of wind energy, some validations of our numerical results, and optimizations, how we can use numerical simulation, or if you heard the term digital wind farms. Now the term digitalization is very popular in different fields. So we also have the concept of digital wind farms, like having a computational method that regulates the real wind farm and can run in parallel while you are operating the wind farm. So I don't know how many of you are familiar with statistics of wind energy, especially in Texas. I wasn't before they hired me in 2013, but Texas, it's actually doing extremely well in wind energy. Everyone thinks about oil, but Texas is one of the states that produce most renewables in the United States. Actually, in terms of produced energy, is number one. In terms of percentage of energy used that comes from wind, is number three, because it uses a lot of energy, and Iowa is actually number one. But we do extremely well. And last year, United States used about 10% of wind energy. So of the energy we used, it's 10%, about 10% came to the wind. And the goal is to arrive to, there are many targets. one that it's a bit far away. It's 2050 to get to 35%, and yeah, you see it's here. We are at the moment about at this point 20% by 2030. There are many challenges to do this, and most of them are logistics, especially land use, production and of the blades. Now, I mean, when you decommission a turbine, you need to get rid of the blades. Now there are techniques to recycle the blades, but we didn't have them before. So you may have what we call cemetery of blades. If you drive to Abilene, you will see a lot of land where there are just old blades. And you see this blue area is the amount of energy that we plan to extract from offshore. At the moment, we are very much behind with respect to Europe. We don't do much of, we don't do much offshore, but as you know, in Massachusetts, things are changing. They are starting to build, and there may be possibilities that also in the Gulf of Mexico, so there will be offshore turbines. The problem of Gulf of Mexico is the wind is relatively low, but with the growing size of the turbine and the proximity to cities like Houston, it's very efficient to have production of energy exactly there. So what is research in wind energy? Well, there is the academic research thinking about vorticity. If you are not an engineer at this, or like swirling flow, and we like to study everything about the dynamics, and we try to write theories about this. But companies and normal customers, they really care about the cost of energy. So one of our major goals is to use science to decrease the cost of energy. And you can put, I like to think about it also in a different way. You build a wind farm, and it's not 100% green, because you're still taking the land, you are spending energy to build the turbines, and then you need to operate it. Then with fluid mechanics analysis, we can produce more than you were expecting, just doing an optimization. And that little portion, that 2%, is really green, because everything existed, and they will operate it anyway. So we are doing an upgrade based on a strategy that you will see at the end. So the cost of energy it's fairly low now in these days in wind energy, and it has been challenged by the price of gas for a long time in the past few years, and but now is actually, it's given the circumstances, it's a very cheap form of energy. So how do you calculate the cost of energy? Well, you need to get the land, so you very likely will do an investment, buy the land, and you will have to pay an interest on the loan that you get. You will have costs related to operation and maintenance, and everything is divided by the amount of energy that you produce over a year. So where we as engineers or scientists can affect the cost of energy, either by increasing the production of energy from the plant, or by reducing the O&M, which means increasing the resilience or the durability of the blades. You will see during the presentations that the wind is not constant in intensity and direction as we may think, but it's always meandering and this causes fluctuating loads on the blades. And if you take, I don't know, a paperclip and you start doing something like this, eventually break. Not because you're very strong, but because you're doing cyclic loads. And the same happened to these machines. So I took a picture of the largest turbines. UK is becoming very, very aggressive. I mean, most of you are Italians, so you know that Denmark is basically producing all the energy from the wind. There are days where Denmark produces more energy than they actually use from the wind, so they sell the excess of energy to the grid. And there are many offshore wind farms that are being built while we speak, and you see the area, it's very big. And I'm not talking about this today, but we can talk about this offline if you're interested at the end. I always question myself, what is the impact of the offshore wind farms on the life in the ocean? We are proposing to do research. It's actually, I always thought it was very detrimental, but you can exploit the mixing induced by the turbines to increase growth of algae that are very active in carbon sequestrations. So if you combine fluid mechanics and biology and ocean engineering, you can really shape the climate. It's just something that we haven't done yet, but it will happen in the future if we are given the opportunity from funding agencies. Now, this is the largest turbine that is being built, and maybe you have seen already this picture. You can compare to the Eiffel Tower or the Chrysler Building. I mean, we're reaching a height that is really significant. So the diameter of the turbine is 260 meters. These are the largest rotating machines that we have ever built. And these produce 12 megawatt. So they don't produce 12 megawatt for 24 hours. There is a capacity factor that for these machines, you can say it's 40%. So they produce, in average, say 5 megawatt. So it would be what, 15,000 Italian houses powered by just one of these. Much less American houses. We all use a lot of air conditioning, but my parents' house in Italy is 3 kilowatts. They have 3 kilowatts, and they cannot exceed that. Otherwise, they cannot use the oven together with something else. So this will power 15,000 houses. Just one. So what is that we do in my research group? Well, we do CFD, computational fluid dynamics. Experimentalists who don't like numerical methods, they call it colored fluid dynamics because we do colorful pictures, but they imply that they don't have much physics. So we want to have the physics, and I normally don't use CFD for that reason, but we try to stick to the physics. And again, how can we, what is the value proposition? It's very hard when we present our study to communicate effectively with companies like Energy Power or any other company, because we are too much academicians and we forget sometimes that you need to have a return of investment. What is the return of investment? Well, by running these simulations, we can predict failure and schedule maintenance. One of the major costs when you have to repair a turbine is that you need to stop it, so it doesn't produce, and you need to wait to get the spare parts. So if you actually can predict and have a very smart maintenance of the turbines, you reduce a lot this cost. Well, we can increase the power production, as I'm going to show you, and also we can also reduce the interest on the investment by mitigating the risk. So we do assessments that give the investors a good figure of what they can, of what the wind farm can produce. So CFD has been around for 100 years or more. You may have seen simulations of the trajectory of hurricanes. You may have seen Formula One, Ferrari cars solved with CFD. Wind energy is a very tough problem because you have a range of scales that goes from texture damage, so millimeters or even less, to the length of the wind farm that, as we have discussed before, the diameter of the largest turbines now is 260 meters. There are not many yet, but if you drive to Panhandle in Texas, there are many 60 meters diameter turbines. Separation is 10 diameters. So by 2 rows, you have already almost 1 kilometer, or half a mile. So you understand that this becomes a very big region where you are extracting energy from the atmosphere. And even if you're not a mechanical engineer, I mean, think about the system. You have the atmosphere that has energy and is flowing over a region. And then at some point you place these big machines that extract energy. And so you are changing the circulation in the atmosphere. When the turbines were very small, it didn't really matter. Now that the turbines are big, there is an interaction between the turbine and the mesoscale circulation. So, does it make sense? The feedback that the turbine is giving to the wind. So, why I'm talking about this? Well, because I'm a modeler and I need to resolve this effect, and at the same time I need to have a big computational domain to solve this effect. So I should have a huge computational domain with a very fine resolution and run my simulations for a very long time. And these things are not possible now. So that's where is the challenge, and we try to model some of the facts and just picking the most important that we need to model. So over the years, I developed my own computational code. It took, it's a very old-fashioned Fortran C code with parallel computing, so MPI. It is like 10,000 lines. Then my students added another 5,000. So it's a big package. It's like if you're not an engineer and you have seen Matrix, when you see all those letters scrolling, that's pretty much it. So we solved the blades, we solved the tower and nacelle, we got the cover of wind energy with this paper done by Christian Santoni, who was a Puerto Rican student. We can solve the topography. I have some slides about that. We recently developed aeroelasticity in the code, so that's the extra 1,000 lines. This was in collaboration with the University of Rome, and we couple it with the mesoscale codes, and this is one of the fundamental publications we did. You may recognize many Italian names. So Umberto Chiri is a professor in Puerto Rico now. He's from Cinque Terre, but student from Pisa. Giacomo Valerio Jungo is a professor, another professor at UT Dallas from Cerignola in Puglia, and studied at the University of Pisa. So we still have a strong tie with the universities in Italy, and we simulated a wind farm in North Texas in the region of Panhandle, and I'll just try to give you an idea of what you have to do to solve these simulations. So, as I said, the wind is not flowing constant. If you look at what people normally do, they do ideal cases where you have the turbines and the wind is perpendicular to the turbines. But that is not really realistic. And this wind farm has an owner that want a real result. So what we did was to run a simulation for entire Texas. Then we take the boundary conditions from the North American mesoscale system. I'm not going to bore you a lot with this, and I'll just give you an overview. What we do is we nest the computational domain into each other. So this is a large domain, 500 kilometers by 500 kilometers with a resolution of 4 kilometers. But then inside we have a smaller one with a better resolution, and so on until we get to a point where we can start seeing the turbines that are these dots. Why we need to do that? Well, because you want to have the variability of the wind, but you cannot afford to do a simulation in this domain with this resolution. We also have another two nested domains. We get to a point where we have a few meters resolution. So this is actually what Valerio does. He's an experimentalist and we collaborate. He developed this mobile LiDAR station. This is a LiDAR, it's a laser that measures velocity. It's probably placed around here. And then he gets a map of the velocity around the wind farm. And it's a laser, so the velocity is a radial velocity because it's calculated with the backscatter of the laser beam. Now, these streaks that you see are called wakes. So if you have a flow over a body, behind the body you have a wake with less velocity. So that's a major problem for wind energy, because if this wake goes on top of the other turbine, then the other turbine extracts much less energy. It's like, imagine you get the first row, you have particles of the wind, they're coming with full energy. Then you take some of the energy and you transform it in electricity. While the particle after the first row have much less energy, and the second row of turbines cannot extract as the first. And that's what we try to avoid with the optimization that I'm going to show you in a second. So this was our numerical simulation. You see, comparison is fairly good. We didn't cheat even if we have friends and both Italians, but the agreement was really surprise. Stable atmosphere, so like at night, and this is during the day. During the day is more complex because the ground heat, and then you have convection, natural convection, and it's very hard to pick these in a numerical simulation. As you see, we have quite a good comparison. Now we did all class of validation. So the blue line is our code, the red line is another code we have with less resolution. The black is the real measurement, in real time that you have at the turbine. So our index of agreement was about 88%. So we were quite happy about this, also because the SCADA data, that is the black line we are comparing with, they have an accuracy of 10%. So you get to a point where you really don't know. I mean, within 5-6%, it's good enough, because they both have an uncertainty, both the experiment and the numerical simulation. And we also capture turbulence. If you are not an engineer, you probably experience turbulence on an airplane sometimes, and you bump. So what is turbulence? In a nutshell, it's a rapid fluctuation of velocity. And the airplane bump because it changed the lift on the wings on a time scale that you feel the vibrations. So this is turbulence that is caused by this rotating machine, plus comes from the atmosphere. And we compare very well with the black. This was a major success of our simulations. And but this was a simple.
It seems that in some of this, for example, in this picture you have that the streak of 2, for example, ends almost perfectly on 3.
Mm-hmm.
Is that, like you designed the position so that this doesn't happen, or at some point?
Oh no, it's just a chance.
It's
the
a
wind,
chance. Okay.
I don't have a video here, but I have other videos of similar cases later. So these change completely, continuously direction. In fact, probably before starting to study wind energy, the first time I saw a picture, I say, why are they putting the turbines so that the wake of the first goes on the second? It's not, they are not.
Okay.
It's the fact is that the wind changes direction, so you always have a direction where the wake goes on the next. Unless you have a wind rose, so you have a wind that is prevalent from one particular wind direction, then you design the turbine to avoid the wake interaction from that direction. But eventually the wind meander. So this is just a snapshot, but this will move here. Well, that's a great question. Panhandle is a relatively easy case because it's very flat. When you do other cases like Portugal, this is called, it's Perdigão. So you cannot see very well from the screen, but this is a ridge and this is another ridge. And there is a turbine and a lot of instruments. It's an experiment they did on purpose to assess the effect of the topography on the turbine. So you have the turbine here, and you have met towers. You see 100 meters, 60 meters. This is a valley, and we did a simulation. The simulation is 3D, but you are just seeing a cross section along this dotted line that you see here. And what you can see here is that there is a shedding of vortices from this little hill that goes on top of the turbine. And if you look at the power production of this turbine, it changes in time. You see how many cycles, and this is related to the. I mean, it's similar to the loads that you can get on the blades. That's a great challenge that is not very well considered in wind energy, because initially they were installing them on simple terrain. Now they're starting to put it everywhere. Then you need to be aware that when you have a complex topography, you may have phenomena like this. And now the wind is coming, you see, from this side. Now I'll show you from the opposite side, okay? So the wind coming from right to left. And look, perfect. So the power is basically constant. So the unsteadiness and the cyclic loads on the turbines happen for the same turbine a different time of the day because the wind changed direction. So when you design, if you are not very careful and you look at this, you may think, well, I don't have fatigue at all. This is great. But then eventually you need to consider all the directions of the wind.
What's the time scale of the...
Okay, I'll tell you. This is 10 meters, 10 minus 1 seconds. So let's say that these are about seconds. So this is about 1 minute.
Okay.
And
This
these
is
are
a
about
few minutes.
3 minutes. So, but the fluctuations are in a much. No, this is the one that is good.
So how accurate the topography has to be for your modeling?
That's another great question. Allow me to answer showing you this.
Especially in the offshore also. The offshore is
The
a
offshore,
major rock.
the offshore is also to some extent it's very difficult. In general, we always thought that offshore is a flat, rigid lid. However, during a storm, you have waves that are generated by the wind and the bathymetry, and they interact with the wind and they interact with the turbines. No one has ever done a real study on this. Mostly, well, if there is a storm, we shut everything down. However, if you have significant waves, it's going to damage the turbines. Now there is a study and something we're trying to work on how to use turbines to mitigate storms. So they extract energy and you can use it to cool down the water and try to diminish the intensity of storms. You're not going to destroy the center of the storm, but you had the Harvey, the hurricane. It's completely different if you have a category 4 or you have a category 2. That's a big difference. So even if you reduce the intensity by 20%, it's going to save life, it's going to reduce the damage significantly. So there is a theory, if you can do a thermodynamic study and 10,000 turbines with 3 megawatts, they will reduce significantly the strength of the iron. This was done by Jacobson at Stanford. And now, at that time, we didn't have the 12 megawatt turbines that we have today. And some people say, well, then you destroy the wind farm. But I think I read they were expecting $90 billion damages in Florida this week. So if you do the math, you actually spend less destroying the turbines and saving, well, first of all, you save life, which is another price. But in addition, you reduce a lot. If you do the math, you actually save money. And in addition, they produce energy for you the entire until they get destroyed. So we are working with a company in Brazil. They have this wind farm, and they contacted us because they have about 9 or 11 turbines here. And they are on a ridge. I don't know if you can see clearly from the slide. Now, we downloaded the topography from the NASA database at 30 meters. We ran all the study, and they were complaining about many of these turbines not working, and we saw that only half of them should have problems. And then they said, well, from your topography, you don't see that there is a rock that you see exactly here. I don't know if you can you see. It's little. It's 10 meters rock. That's because we had 30 meters resolution topography. We didn't have it numerically. Plus, we never thought that we should go so precise. And actually, I'll show you. So this is, we did two gases, one with 2.5 meters resolution, and one is with 30 meters resolution, and we got this rock formation. So this rock, we were looking at mostly the effect of the upstream hill. So the wind is from right to left. You get these eddies. So where you see blue means it's the wake of this hill, and the flow is not straight. It's like spinning. It's highly turbulent. And the first time I saw this picture, before doing the simulation, I said, well, this hill is going to give you troubles. But in addition, this upstream ridge is giving you another wake that it goes on the lower part of the road. They showed us, we have a non-disclosure agreement, so I cannot show this, but the turbines are yawing in real time so quickly because they have all this wind that is changing directions and giving variable loads, and they cannot operate the turbines. They made an investment of $1 million, and they have shut down 5, and 3 are working at 50% capacity. So they cannot extract 3 megawatts, they extract 1.5 because otherwise everything breaks. And the reason is because there is a barrier between academia and scientists and investors in showing that we can understand or we can guide the development of wind farms. I believe this is in all the disciplines. So we should need champions to show that we can explain this. We can explain that you can find a better position for the wakes. So you see we did the gaze without the upstream ridge, and this is to answer again your question. You see randomly, or we say intermittently in fluid mechanics, you get like a blue contours that go up and hit the rotor. But this is terrible for the turbine. That's why it's breaking so quickly. So we can predict that, and we can give better positions. Now fixing this, it's very challenging because the manufacturer is telling them cut the rock. But 10 meters of rock. It's not like I mean
A stone.
it's
pretty
to put
expensive.
explosives. I told them, well, isn't it cheaper to do a foundation and lift this up a little bit so you don't get it? But they told me, hey, every day I shut down the turbine, I lose $10,000. So the major cost is really shutting it down. And I mean, these are 100 meters machines. It's not like you take a screwdriver and okay, it's not an idea closet. So that's the challenge, and it calls for preliminary studies. So we calculated the number that is the damage equivalent load. These are the loads on the turbines, and you can find a figure to, these are qualitative pictures, but you want a number. Can I really operate this? And you see they have 9 turbines, and only one, it's okay. All these other have the loads that are twice what they have taught in the design condition. It's not because the manufacturer built the turbine wrong. It's just the wind condition that the manufacturer considered was different to reality. And so everyone, I mean, no one is guilty. The customer says, oh, these they don't work. And the manufacturer say, well, you are using them in the wrong spot. And let me show you why number 7 works. You see that you have a ridge here, then you have kind of a valley and another ridge. So the flow that comes here and hit this particular turbine, it's very clean. And so it's a miracle that you have one that is okay. I hope they don't see this, but they are nice. We had a good time working together. So you see, they are basically, this is offline. So you bought, the cost is $1 million per megawatt, if you think about it, approximately. I don't know exactly.
So they didn't run this feasibility study before?
Yeah.
No, but you know,
Can you?
I don't want to call names, but I propose, I show these things to many people, even in our own country, well, in our country of origin, and it's sometimes there are others that do computational fluid dynamics at a very cheap price, companies, and they don't have this detail, and they provide a recommendation. And unless you earn the trust of a person, it's very hard, because I cannot do these things for the price that companies charge, running the code that run on a laptop in 1 hour. This runs on a 1,000-watt processor for a month. But
it's worth it at the end.
I mean, this is an investment of maybe at least $30 million. So if you spend $50,000 for a simulation, do you think you are wasting money? That's my point. So yeah, this is, so basically now these 4 are not working, and these 4 are working at 50%. So if you want, it's $18 million sitting on a cliff as for cosmetics. We also do, I was telling you, we can even, you give us the wind farm, and we can improve the power production. We derived, in collaboration with the group of Professor Rodea, who is Argentinian but has family from Sicily, so it's almost partially Italian. This algorithm, this is also patented, and when you try to optimize wind turbines, you have so many uncertainties. I mean, you cannot know exactly what is going to be the atmosphere condition, I mean, there may be many factors. And in my simulations, we are assuming that the machine is working perfectly. What if someone doing maintenance didn't change the oil? There is no way I can control that in my simulation, or even know it. What if you had a lot of insects that damage the leading edge? I mean, we are not at a level that we know exactly perfectly the machine, and we can reproduce the reality on a digital computer. We have uncertainties. So this scheme gives an optimization that is model-free, and it's very simple. It gives a perturbation, for example, to the direction of the turbine, measures the power, does a correlation, and tells the machine in which direction it should go. Okay? So it's like the wind is coming in, imagine the wind is coming in this direction. So ideally you want your turbine perpendicular, but maybe you don't know exactly where the wind is coming. So you tilt the turbine first in one direction, you measure the power, then you tilt in another direction, you measure the power, and then you know how to change the wind direction based on the signals. You just do a mathematical cross correlation. It's fairly easy to get the direction. So the way to increase power production is, you noticed before that the wake was going on the following turbine. So now if you give an angle between the rotor and the incoming wind, the wake steer, so change direction. And then you have the second turbine that is going to produce more. You lose some power from the first because the rotor is not perpendicular to the wind, but you increase a lot the power of the second. And I have an animation. This is a case in Lubbock, in Texas. I want to show you the animation. So you see there is a second turbine here. They are perfectly aligned. These are, this is like our simulation. Now we give a yaw angle, and you see that the wake is steering away from the second. So this is the yaw angle. The red is the power production of the first. The green is the power production of the second. So when you give the yaw angle, this drops because now it's not perpendicular to the wheel, but this increases a lot. So when you do the sum of these two, you produce more power. And you can get up to 10% more power production. I'm running out of time. So another challenge in wind energy is, okay, let's assume that now we solved all the problems. I can do a simulation. If you go to the investor, he wants to know how much you are going to produce in 10 years, because that's the time frame where you want your return of investment. They are supposed to last 20 years. So a simulation of a few minutes won't tell us much. You need to consider the different wind directions, different time of the days, seasons, so these all change. And we found with Umberto, you had a conversation with Umberto, a method to quantify the annual energy production from a set of simulations that we can do. We have published this. It's a lot of math. I call it an elegant interpolation. It's called generalized polynomial cause expansion. We do a lot of simulations varying the wind direction and the wind speed, and then we give the real wind rose, or the probability density function of the wind at that location, and we can extract the power produced over a year. And these are a little graph that we use to quantify that. We did some assessment. This is our code, and our result with respect to measurements are within 5 to 2%. If you run one of these engineering models that I was mentioning before that are very cheap and company use, that's the error you get. And this is on a flat terrain in Lubbock, Texas. If you do this on a complex terrain, it's going to be a completely different figure. So this is another case in Ireland, and they had a similar problem. It seems easy to build a machine, but when they actually build a machine, they may have 1 or 2 degree misalignment of the rotor with the sensor of the direction. You have a sensor that tells you the direction, and then the turbine is chasing the wind to be perpendicular. If you do a 2 degree error, 3 degree error, it's already a big loss. And in this paper, we found a way to actually quantify if you have a yaw error, it's called, the misalignment that you have in the construction, and how to optimize it so that the farm has 2.5% increase in power production. This reduces the cost of energy. So these are all the real cases. So we do a lot of fundamental science, but thanks to the partnership with many companies, and a few are here in Houston, that we have in our wind energy center, we are actually trying to apply this fundamental science to solve real problems and to reduce the cost of energy for real applications. So I'll leave this here, and please let me know if you have questions. Thank you for your attention.
Thanks again to the speaker, and we can continue with comments and questions.
The animated video with the wind farm and the generator. Yeah, this one. So, if you have a limited area, like in this case, right? So if you big blades, they have bigger wings, right?
Yes.
But they produce more power.
Mm-hmm.
So, is there a sweet spot for the size? So, what is the if you do an optimization? I mean,
Oh, the bigger the best.
is always the bigger the better?
Because the power is proportional to cube. So this is a power coefficient. It's normally 0.4, 0.5. It's like lift coefficient kind of. Now this is the area, and the reason why we go bigger and bigger is because by increasing the line, the size of the blade, you increase the area. Now the distance is linear, and this is squared. You know? So let's say that you want to have the distance between two turbines that is 7 diameters, and this goes with the diameter square. So
If you include the cost, is it also, doesn't the cost also include the size?
it depends on the sites, like on the site, because clearly if the land costs a lot more,
I mean the cost to build the blade.
the cost to
build the blade. Is that bigger blades more expensive than smaller blades, or doesn't matter?
Still, it is clearly it's more expensive, but it doesn't go with the square. And we are trying to build the blades in a modular way. So not just one blade of 100 meters, but in chunks, and then you connect them on the side. Because the major problem is actually logistics, because you need to transport the blade to the place. And if you drive to New Mexico, very often you find trucks that carry blades. And when they need to turn, it's a problem, they need to stop. And you need to have drivers that are qualified, they have special, it's not like I jump on a U-Haul and I bring the blades. For offshore, you need the ships. And you don't have many available to carry the blades to the sites where you need to build. So you need storage at the harbor, but you need a lot. So a big challenge when you go towards 200 meters is the logistics, and for this reason many people are studying. It's more material science than what I do, but like splitting the turbines in pieces. Even for recycling, there are many ideas of how to use it. Even the last I read is playground for kids using blades and making boards. But and the other thing is, if you go big, the velocity is higher. So you normally, when you go at 100 meters, you also increase the velocity. Now there is something that I don't want to be arrogant, but I think we should study more. It's the aeroelasticity, because all the elastic effects that we consider so far are related to the small blades. Now, if you go to 200 meters, do you guys know aeroelasticity? Like it's the coupling between the wind and the deformation. So, like if this is the blade, I have the wind that goes on top of the blade and will give an aerodynamic force. So the blade will deform, will deflect. By doing that, we'll change the angle of attack with respect to the wind. And this is a feedback. So it's a nonlinear process that may cause instabilities. Flutter, I mean, the first airplanes had a lot of problems for flutters. This is similar. Now, we do know what happened for small blades, but when you go big, maybe we need to rethink the tools we are using to design and include more sophisticated simulations like this to account for deformation. So I cannot actually, I mean, maybe your question, it's very deep, and I can answer. The way we are building, the bigger the best. We may discover that the cost of the blade to go high and account for extra effect of elasticity, it's higher than we expected, but we don't know that yet.
How often do you run the maintenance here? You send engineers to the ground to check the turbines, and also is it monitoring the stability of the pillars? I don't know the technical term.
They have many sensors, and
Okay.
they have a control room where they get warnings from this. Now the world is moving towards the market is moving towards like automated surveys. I have seen robots that enter into the blade. The blades are actually big. I mean, it's not a little blade. You can walk inside, and you have a little robot like I don't know. If you have a pool, the little robot that cleans the pool, you have one entering in the blade, and with laser is giving you the old geometry to find if you have problems. There are others that want to use micro UAV, flying them and taking pictures of the blade. Clearly, it's a challenge. Once I heard a presentation from a person from GE, and she said if we were to put a sticker GE on each turbine we have built in the world, it will take us 10 years or something like that. I mean, she was implying that they have so many turbines that manually and visually going to inspection everything, it's basically impossible. That's why if you have models or sensors that help you in that, it's a big advantage.
Countries that are using the aeolic system like the Netherlands for obvious reasons. Do you think that in Italy is there enough room to increase the aeolic power or not?
Well, first of all, I think Enel Green Power it's a great company. They have a good market in the world. They are not small. I mean, they are one of the leaders in the world. Maybe are among top 10. They do a lot of business in Brazil, I think, and Spain. In addition, maybe more than Italy actually. I think there is a lot of potential in Italy, but from what I heard, there are people who don't want to put them on the ocean because they don't like to see a turbine. So it's more a political issue than an engineeristic issue. So, I mean, my personal opinion, especially nowadays, renewable, many countries have renewables. They are more isotropic than fossil fuel, right? Fossil than coal than oil. So it can only be better if more countries have access to energy than just having all the resources in one place. So in Italy has sun and wind. Even if you don't go like Denmark, but having 30%, it's doable. It's just, but it's a political decision. You need to decide it from the top. And then the other thing is you need to break the barrier between people who decide and people who know where you should put the turbines and make them talk. It seems so simple and trivial, but it's the major challenge, I think. I hear the stories that people installed turbines wherever because they were getting the benefits tax deductions. So they didn't really care about optimizing. They were already making a profit by just placing the turbines in a random place. So if you want to change the economy to some extent the system, I think you need to use studies like this and many other studies like this to have informed decisions.
How does the cost of per kilowatt hour for the solar compared to aeolic? I mean, which one is the and if you cover the same area with solar panels, which one produces more power?
I may be biased a little bit because I mostly work in wind. Okay, I don't know the latest solar energy research, but up to a few years ago, in terms of energy that you require to produce your turbine, I mean, let's put it this way. I mean, if you are really an ecologist, you wouldn't worry too much about money, but you will worry that the turbine that you build produce the energy that you use to build it as fast as possible, right? And I think for wind turbine, if I'm not mistaken, in 5 years, 6 years, it gives you back the energy that you used to produce. Maybe now with the growing sites, it's even less. So they last 20 years, so at least 20 years. So maybe you get 15 years of real green energy. The first 5 years, it's to build them. I think solar, it's a little bit more, so it's like 7 years or something like that. In terms of the impact, I don't know, it's my opinion, it's you can still do agriculture here.
Yeah.
When you go over with solar, you basically have used the land.
Yeah.
If you go to Panhandle, to Abilene, they have cows that actually walk while if you have a visit on Sweetwater, I went this summer and you have cows everywhere. So you can still do that. In terms of cost, now, last time I checked, on-site, inland wind energy, I think was $20 per megawatt, so 2 cents. So it's really cheap. I pay 20. My is the bill now. So there used to be a time where the cost of wind energy was too high, and everyone was saying, "Oh, you'll never make it because it's now it's not only good for the environment; it's even good for your money." And I think I read on the Italian newspapers that because of the increase of cost of gas, then all the other sources of energy were making huge profits because they were paid proportionally. But I think now they are doing it different. So the amount of energy that you're producing from wind and solar is actually reducing the cost that you pay in on your bill.
Another question, excuse me, perhaps it's a silly question, but you are an expert of wind but also of fluid dynamics. So is it possible to think in future to translate this kind of systems to underwater systems in
There are.
the rivers?
There are already hydrokinetic
There are
turbines, but they are small and they produce much less. So they are small turbines like this size. They use a lot in Florida, for example. They have the Keys, and so they don't produce that much. But everything is useful, and as well as it depends how close you are to transmission is a problem, right? In Panhandle, you don't use all the energy that you produce.
Questo progetto.
Oh, okay.
As a timeout.
So the major advantage of offshore in the United States, especially in the Gulf, is not that you produce like your efficiency is better than what you have in other places. Is that you have a huge center like Houston that is right there, and so transmission cost is very low. That's why in Denmark is so good, because they live there. It's produced there, they use it, and if they have a little bit more, Europe is so clustered, they have Germany so close that they use so much energy. So sometimes even the hydrokinetic turbine may make sense, because for particular places, if you produce there and the people are using the energy there, and think about after an hurricane, if you can produce the coastal population that doesn't have the transmission because it's broken, but you can have the local microgrid that can sustain. So they are all good initiatives. So I'm not a guy, so I forget the other renewable. There are wave converters that also are used. Many studies in Massachusetts. They just take the energy from the wave and produce electricity.
What is the figure of merit for the efficiency of a turbine? Because for solar power it's kind of straightforward. The intensity comes into.
I would say the power coefficient of the turbine.
So here, what do you consider your input?
So it's this guy. You cannot. It's the number that it's figure of merit of the aerodynamics.
Okay.
So the power, the amount of power that you're able to convert in energy cannot go to one, and I can, if you have 1 minute, like if you have a turbine, it's like a little tricky. You have incoming wind, let's say has a velocity of 10 meters per second. Then in the wake you have 7 meters per second, and 3 meters per second cube is the one that is used to extract, to make energy. So this coefficient tells you how much of this difference is converted in energy. Now, one cool thing, well, if the perfect turbine will give me 0 meters per second downstream so that I transform all the wind into energy. But it's impossible because you need to have conservation of mass. So the same mass that passed through this stream tube needs to flow out here. So normally, so that's why you cannot have an efficiency close to 1. So you can only, you cannot transform all the power of the wind into energy. You just transform something around 45% on an isolated turbine. The optimization of the blade give you very little on this. So you gain much more by designing the farm in a smart way rather than having a better blade. But for example, there are blades with vortex generators that give you a little extra production. Winglet at the end, so like if you have a blade, you have like a plate like this that prevent what we call thick vortices. So there are little things. This will be your figure of merit. And if you buy a turbine, you get a curve that is the power curve of the turbine, that you have velocity and power. So it does something like this. This is region 2, which is this formula I wrote before, 1/2 rho v cube area CP. And then you have region 1, where the wind is too weak so that the turbine doesn't move. And this becomes region 3, the wind is too strong and will produce too much torque that will melt the generator. So it will spin too fast and create too much energy that will destroy the generator. Also the structural loads will be high. So when you get to region 3, then automatically the control system pitch the blade to produce less. So you curtail to the production. And sometimes of the day, the authority, ERCOT, can tell you you are producing too much and you are causing trouble on the grid, so shut down or reduce your production. So you change the pitch of your blade, and then, for example, instead of having these,